So today we have this Fibonacci series with DP. We have already solved this with recursion, and today we are looking with DP. So Fibonacci series, as you all know, is this repeating numbers from the last. Like you already know what a Fibonacci is. Now what DP basically is, DP is a combination of recursion plus memorization. I'll explain you what this exactly is, because what recursion do is recursion generally shows TLE most of the time in online compiler. Like if you are coding on LeetCode, GFG or HackerRank, it will mostly show TLE because the tree which we make in recursion generally goes so deep down that it goes out of bound, and the constraint which are provided, like recursion is generally not effective in coding, and like it's effective in coding, but when doing on the online compilers you'll generally get TLE because the constraints are high. And memorization is, like, I'll explain it down. So recursion gives TLE most of the time, and DP is a combination of recursion plus memorization. This thing is new. This thing, what this thing does is this improves the recursion to make it effective, so that we do not give TLE. TLE is time limit exceed error, and generally space also exceeds. So DP is not a data structure like Q and all. It's not a data structure. It's a technique to reduce time complexity, increase computation speed. That's it. It's nothing special like arrays, data, and nothing. It's not a data structure. It's just a technique which is very helpful. Let's say we need to find 100th Fibonacci number. 100th Fibonacci number. It's really huge. That's what she said. I'll leave it. So let's find the first five. Like let's find the fifth Fibonacci first. So the basic idea which we all know is, like, if a number is how the just a second, how Fibonacci works: 1, 2, 3, and 5. So any number is the sum of previous two elements. 3 is the sum of previous two elements. 2 is the sum of previous two elements. So n minus 1 plus n minus 2. This is the formula. Let's get this out. Yeah. So this n minus 1 thing, let's draw the tree for this. So here's the tree. And for first 5 1, f of 5 will be called, and recursively it will call 4 and 3 because sum of previous two. This is f of n minus 1 and f of n minus 2. Just remember this. This is the sum. So n minus 1, 5 minus 1 is 4, and minus 2 is 3. So f of 3 and f of 4. Again, f of 4 will recursively call the last two elements for f of 3 and f of 2, minus 1, minus 2. Then f of 3 will call f of 2 and f of 1, and then f of 2 will finally call f of 1 and f of 0, which will be our base condition, because if n is equals to 0 and n is equals to 1, our answer is n only. Return n only. Our answer is n, because for n it's 0, the answer is 0, and for if it's 1, the answer is 1. So this thing returns 0, this thing returns 1. Addition of them returns 1 to the second position, and we can see here 0, 1. Second position is this thing. If you'll start from 0, then obviously second position will be this, but this is first and second. So second value is 1, which is obviously correct. First value is also 1. So this one and this one, these two are done. Now let's hop on to this thing, f of 3. 2 and addition of f of 1. F of 1, it will again compute. We already know the value of f of 1 is 1, but it will again compute going out to the 0, and it will not like go beyond this. So this will return 1 only. And just a second, this should be 1, I guess. F of 0, 0, 1, 2, 3. We are computing from 1, 2. Yeah, this is 0, but we generally do not write it. This is 0, 0, 1, 2. Like it goes like this. So the fifth number, the second number for that the same thing, the array one. 0, 1, 2, 3, 4. This is the array index, and in real life index, how we do it? This is 1, 2, 3, 4, 5. So if someone asks you that second number of Fibonacci, it's always 1. So this will compute F0, then it will return to F1, and then it will return to F3. Then sum of these two will be F3. Sum of these two. This thing and this thing will compute to F3. We need to go down to this thing. We have already computed this thing, but we are again finding this thing. So F3 would be 1, 1 and 2. So F3 would be 2 because 1 from here, 1 from here, this thing will be 2. Now again, F3 is computed, F3 will return the value 2. Will come back to F4, but F4 has already passed this F2 thing. This will F2 will again call F1 and F0 because those minus minus thing, F1 and F0. Again, this will return 0. This will return 1 and 1, 1 and 0. F2 will be again 1. Just a second, 1, 0. This thing will be again 1, and this thing will return 1. This is already 2. 2 plus 1. This thing will be 3. So F5. F5 will again compute all these values, and now you can see one thing. Uh, Let me just erase all this. It will be much clearer. Yep, one thing you can see, we have computed F4, F3, F2, F1, and F0 already once. Okay, but now if you'll see the whole tree, what we need to compute F3 again. Yes, we need to F2 again, F1 again, F0. This whole thing, this whole thing needs to be, even this thing also. These thing needs to be computed again because, and even these things also, like while going down, we have already calculated all the values, but in recursion, this is the only factor which gives TLE that we need to compute thing again and again. So what this thing does is, let me just erase this. Yep. So the old time complexity. Yep. So the old time complexity of this tree, whenever we are running this tree, we have to again hit F0, F0 again, F1 again. This will return the base case, and F5. Finally, this will return with the value 1, 1, 2, 3, and 5. In normal indexing, this will be first, second, third, fourth, fifth element. In array indexing, this will be fourth element, obviously. This thing. So fifth element would be 5, fourth element would be 3. So for finding F5, this much big tree computer needs to compute. Obviously computer is fast, but just imagine a tree for F100 and doing it with recursion. It's it's almost impossible. It's almost impossible to find this Fibonacci 100 number by using a simple computer because the computation tree will be so big it will keep calculating, and there is no need to calculate it again and again because we have already calculated F4, F3, F2, F1 here. Why we are again calculating this whole thing? So here introduces the DP concept, and which reduces the new time complexity to O of n. Earlier it was 2 raised to the power n complexity because there were n computations and they like it's something. Or if you want, I can solve this whole time complexity, but just leave it for now. And this was the tree. So imagine if we need to find for the 100th tree, it's almost impossible. So how DP reduces the time complexity? That's the base case, and that's the main thing. So DP reduces by using memos. Memos is a kind of notepad, like we keep a notepad. So memo is a notepad. What this notepad does is this keeps the value, this keeps the count, this keeps the exact count of value which we have calculated already, like F0, F1, F2, F3, F4. We have calculated. I'll just draw this thing. In this loop, we have already calculated these four values, even F0 also. We have already calculated F0, like F1 will call F0 again, and this will call nothing. So we have already calculated these five values, and we'll just store them in a notepad before heading towards these values. Why? I'll just tell you. So imagine this is our memo pad and we have already our computed value stored here 0, 1, 2, something, something like this. Now what will happen when this F5 will head toward F3, instead of going all the way to F0, F0, F1, F2, instead of going all the way down to the 3, we'll just call out our value f3 equals to 2, and this whole computation will be reduced. This whole computation will be saved, and directly the value 2 will be returned. This is the biggest impact of DP. It just saves your computing space and time. I'll just explain how it does. So we make an array called DP. It's my array, and this array is obviously the size of n plus 1 size. Like if we have n equals to 5, so we'll create a 6 size array, because n plus 1 we need to compute one additional value. I'll just explain you. This is 1 2 3 4 5 6. Sorry, we are to find f5, so we have created a 6 bucket of array. Now there are two conditions which we need to check for DP. First, before the condition, what we need to do, we need to fill all this array with -1. Like we need to fill this with something which can never come in Fibonacci. Like Fibonacci always start from 0 1 1 2 3 5 8, this now -1, -10, -20. These value can never occur in Fibonacci. So you can fill this with any value, which will just never occur. So I filled all my array of like DP with -1. Now there are two conditions which we need to check. I did not explain to you those, I guess. Yep. These are the two conditions. First is storing the computed value hand to hand in our array. This array is completely filled with -1. We have calculated that f0 is equals to 0. On 0 we have -1. Change this -1 to 0. Now we have 0 value on the 0th index. Again change this 1 to the value here. I'll just change this thing to 1 because we have calculated. Change this to 1, and let them, like, let's leave 3 4 and 5 for further further computation. You'll just get to know why. So we have changed these -1 to the value we have computed. Second thing is, if any place is not equals to -1, which is if we have found the values for any of the indexes, like for 0 1 2 we have our values, which means it already got filled and we need to return the value. We need to return the value, this thing, f3. Just imagine if f3 value we already know is 2, and this array is filled with 2, so whenever f3 will be called, instead of going whole down to the tree, like instead of going whole down and adding the computation power, why can't we just return the value 2 from here? That's the thing I've said here. If in any place dp in the array is not equals to 1, not equals to 1 means we have already found the value and we have already computed. So just return, do not go any further beyond. We'll get to know this in code. Just a second. Yes, you'll get to know this in code. So if in any place we have -1, which means it has not been calculated yet, just calculate it. And if it is already been calculated, like 1 2 0 1, it's already calculated, then just put the values here and you are good to go. So that's how DP works. I guess you got an thorough idea from this. And anything else to explain? Yeah, this time complexity thing, ON thing. Earlier we were computing for whole our graph. Like earlier we were computing for whole the graph, but now what we need to do, we need to compute this thing. Like this is the basic, at least we need to find all these values now, all these memo. So at least we need to find them once before storing. Now we have found all these values. Our n was 5. These values uh, till this 1 1 2 3 4 5, and this will run n time. Like if n will be 6, this will run 6 times. So n, this will run n times. Now to run a tree we need to run the alternate thing also, like this value and this one. I'll just use some other color. Let's support LGBT. Yep, this thing. uh, yep, we need to calculate, LGBT is lagging. We need to calculate 1 2 3 4, which is n minus 1 here. We need to find four values also, because uh, if you are computing this thing, you need to compute left and right also, then it will provide the sum. If you are computing this thing, you need to find left and right, then it will provide the sum. For this thing also, left and right. So if you need to find all these four values, 1 2 3 4 5, you need to find the rightmost elements also, this thing. And for this, so there are n minus 1 and n here. I'll just explain it here. So total number of iteration, we are n minus 1 plus n, which is 2n minus 1, which eventually is written as O of n, because these numbers are very small. We generally calculate time complexity for very large number, like for 10 0 0 0 0 7. So minus 1 and into 2 won't do anything for this. So constants are ignored, and the new time complexity would be On, which is the optimal for this thing. Earlier we were going to 2 raised to the power n. So I'll just show you the code. Here's the code. The same problem, nth Fibonacci number, and they want us to find it in 0 and n. This can be only done by DP, otherwise the time complexity using iterative solution or recursion, it will directly show TLA, I'm pretty sure, because constraints 1000. And if you just imagine making a 1000 constraint tree, like 1000 number tree, and it's also saying since the answer can be very large, return the answer modulo. I'll just explain it. So they have passed this n number. For example, n is 5 here, which I have just explained. So fifth is only fifth number. Now we have declared a new DP. We have declared a array, a new DP with n plus 1 size. N plus 1 because we need to store an extra element. Now for int I equals to 0, this is the whole loop, and we have filled this whole DP with minus 1 thing, which I have told already earlier. Now return Fibo. Fibo is our function. We have passed our DP, this minus 1 filled array, and our number. Now let's go up. This thing, this is the base case. And this is the base case which we already use in recursion. If n is equals to 0 and n is equals to 1, which is basically if it's 0th or 1th, the number is always equals to uh, you know already 0 comma 1 comma 1 comma 2. So 0th index 0, first index first, second index 2. We starts generally from second index because 0 and 1 are already provided. So what we have done, we have filled this DP of 0. Let me just change the DP of 0 with n only, So the 0th index is, earlier it was minus 1, now it's 0. And we have returned n from here. Like if this thing, I'll just explain this again. For DP of 1 equals to, we have filled this with 1 because uh, this is the condition. If n is equals to 0 and n is equals to 1, we have filled this with 1. So that's how this thing works. Now on 0 and 1th, we do not have minus 1, we have 0 and 1. Hope you'll explain this. Hope you'll get this thing. Now ignore this. If dp of any number is not equals to minus 1, which means we have already computed the number, so just return the number. You'll get this thing also. These are afterward step. Main step is this thing. Fibo of n minus 1 plus Fibo of n minus 2. Just look at this thing. N minus 1, n minus 2. Fibo recursively calling our function. Fibo of n minus 1, n minus 2. Same thing. For 5, things are going like 4 plus 3. This thing. So we are also passing our DP because obviously DP is this array is important for minus 1 and all the value we have filled. Now this thing, return DP. This is what I have told you, storing the number hand to hand, storing the number. For example, you have found for f of 1, you have found the answer is 1. You have found this. Now just go and store this in the 1, which is obviously we have stored this here. Like let's take it for 3. We have found that 3 is equals to 2, because it's like 1 comma 1 comma 2. 0 1 2 3. If you will take 0 1 2, this will be 2, and if you will take the indexing from 1 1 2 and 3, so this is 2. Now f of 3 is equals to 2. Here also f of 3, dp of 3 will be filled with this answer. This answer gives you 2. This answer gives you 2. This dp will be filled with 2. Just for further case, we are creating our memo first. This dp will be this like array of third index will be filled with 2. Similarly, array of fourth index will be filled with something something. Now, the left tree is done. What I've shown you, the left tree is done. Now we are heading for the rightmost trees. Now our array is filled with, like for example, this is my array dp, and this is already filled with 1 comma 1 comma 2 comma 3 and 4. So half tree is already calculated. Now whenever we will visit the rightmost tree, which I have shown you, whenever we will visit the rightmost tree, these values will be checked here. If these are not equals to -1, none of the value of them are equals to -1. So this will return the value directly without computing more. This was the thing which DP was doing. This will just return directly F3, which I have written. Let me just show you. I hope this don't crash. Yep. This f of 3 thing, it will find out that okay, dp of 3 is already, we are having a value and it's not equals to -1. So let's just return, instead of doing all this computation, let's just return from here. This will return 2, not z. Of course I have written 2 here. This will return 2. This thing, let me just remove this. This thing will just check the base case, and base take 0 equals to, obviously 0 equals to 0, 1 is equals to 1. So, and yeah, this modulo thing is, when answer gets too large, we are advised to modulus with the provided numbers, so it generally decreases your number. Like modulus symbol provides you with the reminder. So until your number computation is greater than this will works fine, and the constraints are given accordingly that this will not exceed the given value. So I hope everything is clear here, and let's just run this. dp, yep, this should be equals to n. Yep, execution time 0.0. And if you'll do this with recursion or iteration, this time will increase. And definitely for recursion, it won't take, like for n equals to 1000, not possible. Not not in any condition it will take the 1000. It fails on 100 only. So this was the code.